Welcome to Espresso on Electronics, quick sips of EDA wisdom. I'm your host Anika Sunda, and joining me today again is Yoshi Watanabe. Yoshi is a distinguished engineer at Cadence, and he's working at one of the most cutting-edge technologies, which is how can SimAI help you solve your pain points and challenges, which is bug hunting and coverage maximization. So we all remember that Yoshi spoke about this technology, SimAI, in the past, but today he's going to shed more light and talk about the bug hunting aspect. Welcome to the show, Yoshi.
Well, thank you very much, Anika. Thank you very much for having me again.
So Yoshi, diving down and not wasting much of time, could you let us know what is this technology called bug hunting in SimAI?
Yes, it is a technology to synthesize regression that exposed failures in RTL or test bench during logic simulations. A regression in this context is a set of simulations. Verification engineers create a regression, and then they simulate it many times regularly. This regression or test bench that they built had some degree of randomness, so that whenever they simulate it, they automatically generate many different kinds of the test scenarios to verify your designs. Now, in our last podcast, we talked about coverage maximization, right? And the coverage maximization is a work that simulates exhaustively those design conditions that the verification engineers think important and necessary in order to sign off their designs. But their ultimate goal in verification is to find bugs and fix them, right? Coverage is a means that helps them achieve this goal. So in SimAI, not only we provide a technology for coverage maximization, but also a technology to explicitly stress failures and corner cases to expose bugs.
So, Yoshi, what do you really mean by stressing failures?
Yeah, so when people write RTL or test bench, they typically also write some sort of error conditions. These are some sort of checks against some wrong behaviors, unexpected behaviors. They could be assertions in RTL or UVM errors, some kind of checks like you send a packet, but you didn't receive acknowledgement signal, or you did receive it, but not within the particular time window that you're expecting, or so on and so forth. When a simulation creates a test scenario during this regression, and then if it end up with that kind of the erroneous condition, and then simulation fails, typically with some sort of the explanation about the nature of the failures, like acknowledgement signal did not come back in time or so on. And the SimAI synthesizes a regression that produces lots of test scenarios that end up with those erroneous conditions lot, especially those that have not been seen before or seen, but only very rarely. And that's what we mean by stressing failures. Now,
absolutely,
in the whole verification project, that we learned that there are multiple phases where those stressing failures become important. One is when they want to freeze RTL code. And this is often before the coverage closure, or even before starting coverage. The coverage model may not be defined yet. Another phase is after closing the coverage. Now RTL is frozen, test bench are mature, tests are well defined, and they already closed coverage, and so really stressing many corner cases. But empirically, they know that there are some hidden bugs in somewhere in the design, and so they go after intensively the lots of simulations to try to expose those hidden bugs. And SimAI works on those different phases. If there is a coverage information, and then SimAI uses the coverage information to actually help exposing bugs or stressing failures. And if there is no coverage available, then that's okay. Technology uses existing error conditions, learn from it, stress them, and then expose more failures.
So Yoshi, I'm sure the listeners must be thinking about what kind of bugs does it expose? Is it RTL bugs? Is it test bench bugs? I mean, what kind of bugs have you seen in the past?
Yeah, both kinds. That there are many test bench bugs in the early phases. And when there are lots of failures, the easy failures, they usually do not use our technology because they have enough failures, they have enough things to debug. When it comes to very rare failures, it's difficult to reproduce, or they think that they already fixed many bugs and they're hunting for some hidden bugs. That's where they use our the technology. And in those cases, they find some of those test bench bugs, but also that they identify the RTL bugs. So we see the both kinds of bugs.
That's awesome.
Yeah.
Also, Yoshi, this was not easy, right? I mean, developing AI solutions, I'm sure that there might be a lot of hard work and permutation combination that might have gone this, right? Because developing
Absolutely.
algorithm is not easy.
Right.
So how did you
Right.
guys, talk about a little bit more about how was this done? What AI solutions did you?
Yeah. So, building those tools or algorithms is really challenging. First of all, this problem, as you say, is very difficult problem, right? And in some sense, this is even more difficult than coverage maximization, which is already known to be a very difficult problem. And the reason is that you really do not know where those bugs are, right? If you know about the bugs, you probably have already fixed them, right? And that is different from coverage maximization or coverage holes. Coverage holes are something that you defined as a design conditions or bins. It's just that you have not been able to create test scenarios to hit those design conditions. I wouldn't say this is an easy problem. It's very hard, but at least you know the target. That is the design condition that you're shooting for. But for bug hunting, there is no such explicit target. It is not like you know the target, but the target has not been hit. You really do not know where those bugs are, what kind of targets that you're shooting for. And clearly you're not able to just shoot randomly in the woods. And so you need to do something. But those verification engineers have done already many things. Those are the experts. Not only they know about their design and test bench and the spec, but they have lots of experiences. Like from the past project, they know those kind of the erroneous scenarios where typically those corner case bugs are still there. And so they use those experiences and then create really nice matured regressions, and they spend lots of time. So for somebody like us who come up with a tool to go beyond those expert human doing is extremely difficult task. So we spend lots of time studying how people doing those things. And at the end, we basically developed two kinds of algorithms in SimAI. One is that this is the wisdom that the people use, learn from failures. So that the SimAI analyzes the data coming out from Xcelium Logic Simulator. When those customers' regressions are simulated, Xcelium produces lots of data. And the first algorithm is a proprietary algorithm that extracts some patterns from simulation when simulation fails, and then identify those patterns that are kind of unique or particular, the fail scenarios, and that are not really seen unless the simulation actually fails in that particular way. So that's like a signature of the failures. And so that's the pattern extraction. And the other thing is to stress corners. This is another wisdom that the human know that typically those hidden bugs are there in those corner cases, the cases where they are not being able to simulate intensively. So SimAI does the same thing. It learns from such corner case scenarios again, extract patterns that kind of salient to those the corner case scenarios that are not seen unless it goes to those deep corner cases. And so that those are the two different kinds of the algorithms, learn from failures and then going after corner cases. Now, our really goal is to expose bugs, right? And so it's not really like stressing corners and so on. And so that what we did was to combine those extracted patterns and the randomness to explore new design conditions in proximity of those corner cases. And that's really the strength of our technology. On one hand, our tool analyzes the data, and then those extracts those simulation patterns that enables you to penetrate the design deep in those erroneous corner case states, together with the randomness that are inherited in the test bench or tests that were created by those human expert verification engineers. By doing so, our technology are able to penetrate the design deep and then explore to expose some new design states and possibly bugs. And that's what we do.
Thank you, Yoshi. Sounds really interesting. Could you also walk our listeners through the results of SimAI?
Yeah. So again, that we collaborated a lot with some early adopter customers, and the results are really good and encouraging. We typically see two things. One is that the regressions synthesized by SimAI using this technology produce multiple new failure signatures that have not been seen. And this does not really mean that you expose new bugs. Some of those failure signatures may be new, but they may be caused by the same bugs that the human have already found before. But there are those failures that are caused by bugs that they have never been seen. And even for those bugs that have been seen, maybe this is a new test scenarios to end up with those cases. And so that gives us good opportunities for people to analyze. The second thing is that we amplify extremely rare failures. When you simulate the customer's regressions, there are some failures, but some of them are extremely rare. The failure rates are really low, like 0.001%. So in order to produce this failure, you have to simulate your regression many, many times, like 100,000 times. So when you see that failure, it's really precious. And so you really want to keep it and you want to analyze it. But because it's so precious, it's very difficult to reproduce. When you want to ask the question, is there any other way is this the only way that this bug happens? Or is there any way that the same failure could be reproduced? But since it's very rare, you have to try many times. And SimAI actually can learn from such extremely rare events or failures, and then be able to create test scenarios which are different from each other, but all lead to the same exact failure signature. In that way, this gives more opportunities to human verification engineers to analyze those very rare failures, but the different ways, so that they can, look at the design from the different angles, the mechanism of the failures in the different ways, and possibly with this course of the work that they might find some new critical bugs, or they could create the tests which are dedicated for such extremely rare case, but can stress those relevant design states more intensively. And overall, we are very excited about this technology, and it's really great to see more and more people now start to use this technology for hunting bugs in their designs.
Thank you, Yoshi. Really. I mean, all that you've spoken, I think it is, end of the day, it's helping our DB engineers to maximize their productivity, right?
Yes,
They
yeah,
want to
that's a
sleep
great.
well in the night and not be like, oh, I think, there's a bug and then it pops up near to the tape out, right? I mean, those nightmares, it's a nightmare, right?
Exactly. And, this is really the great way to extract the power of their randomness and tests in such a way that by data analysis, you can actually steer the scenarios into those deep states and expose the new scenarios and the bugs. And so that's really the good that, take advantage of the human experts by combining with the data analysis power driven by AI.
Thank you, Yoshi. It's been a pleasure having you on the show.
Thank you very much. Yes.
And thanks to our listeners for tuning in. Keep your circuits connected and your ideas flowing until we meet again on Espresso and Electronics. Stay innovative.